Justin Miller, Oxford College Physics here. What the heck is this? It looks like some fascinating apparatus, does it not? This is known as the Atwood Machine, and it was utilized to study and understand the notion of net force and accelerations produced. So what we want to do is kind of understand this Atwood Machine and, well, be able to appreciate it as a system itself. So what do we have here? We've got a string, one single string here, and we've got two different masses attached to it. Mass on this side, mass on this side. And right now, these two masses are equal. This is 100 grams altogether, this is 100 grams altogether. And what do we know? Is it moving up or down when I let go of it? No, it stays the same, which means that individually, the net force on this mass must be equal to 0, and the net force on this mass must be equal to 0. And then we ask ourselves, well, what forces are acting on these individual masses here? Well, we look at this mass, we got the string pulling it up, and we got gravity pulling it down. And likewise, on this mass, we've got the string pulling it up, and gravity pulling it down. So individually, both of these masses have the same two forces, in a sense, acting on them. Force of tension and the force due to gravity. Well, I don't want to necessarily say the same because we could make them different, right? So what happens if I say I go ahead and add an extra mass on this side? Well, what do we have happening now? Well, if I take this system and I were to let go of it with this heavier mass or greater mass elevated, what's going to happen? You say, well, this one's heavier, it's going to go down, this one's going to go up. And that's exactly what happens, right? I let go of it from rest, and it undergoes an acceleration. This one accelerates down, this one accelerates up. And what do we note about their accelerations? Well, these two objects are coupled. They are tied together via this string here. They must exhibit similar types of changes in motion. Now, the direction is going to be different because one goes down, one goes up. But they must undergo the same changes over the same time intervals. That is to say, if this one moves, say, I don't know, 5 centimeters down, this one moves 5 centimeters up. And what time interval does that occur over? The same time interval for both of them, right? This one moves down over 1 second, this one moves up the same distance over 1 second. I do this one fast, this one goes fast. I do this one slow, this one goes slow. That is, they have to have the same characterizations or same characteristics of motion and changes thereof. Because again, they're coupled. So this is a coupled system. And there's all sorts of variations of coupled system, but this is kind of the most famous in a sense and the easiest to understand, we'll say. So what we want to do is analyze this system and see if we can develop some way of understanding the overall acceleration of these masses. That's the underlying goal here. So if the masses are the same, we get no acceleration. As the mass imbalance gets greater and greater, when we add another mass on here, it's greater and greater, what are we going to get? A greater and greater acceleration, right? So this is what we want to have the ability to solve out. So what we want to do is just go ahead and approach a coupled mass system. Now the thing with this is we have to be a little bit careful. These masses are coupled together by a string, that's right, and they undergo similar changes in motion, just directionally they're different. But individually, it's the net force on this mass that produces its acceleration, and it is the net force on this mass that produces its acceleration. So we got to treat these as separate masses and then utilize that they are coupled together and there are similarities in their changes in motion. And then utilize that to figure out the overall consequence of the system, dependent on the mass imbalance. So that's exactly what we're going to do, solve out the Atwood machine. So let us go ahead and do that. Let me move this out of the way. Whoa. I'll stick that right there. And I'll move this. Fantastic. Screw this table back a little bit. There we go. So, we want to look at the Atwood machine. I need to put an exclamation point because I like it. All right, so I could draw out a little schematic of what we got going on, maybe a simpler version of this. But we have some sort of pulley here. We've got a mass number 1, and we've got a mass number 2. So this is just a pulley that redirects the forces. We got an M1 and we got an M2. And in terms of these individual masses, what do we have? Well, we've got a force of gravity acting on mass number 1. Let's call that Fg1 hat. We've got a force of gravity acting on mass number 2, Fg2 hat. We've also got a force of tension acting on each of these masses individually. We've got the force of tension transmitted this way. We'll call that T1 hat. We've got the force of tension on this one transmitted this way, T2 hat. So this is what we have individually regarding these two masses. Ignoring any air resistance, no other forces acting on them, just the force of tension and the force due to gravity. So what we want to do is, again, treat both of these masses separately to begin with. Because again, it's the net force on the individual masses that produces the individual masses' acceleration. So we can look at mass number 1. What do we have with this? Well, we go back to Newton's second law, which says that the net force on mass number 1, so I'll put a little subscript there, produces the acceleration a hat 1 of mass number 1. Great. What else can we say? Well, we can say what the net force is composed of, right? The net force acting on mass number 1 is the vector sum of T1 hat and Fg1 hat. T1 hat plus Fg1 hat. What does this give us? Well, this gives us explicitly that T1 hat plus Fg1 hat must be equal to M1 A1 hat. Fantastic. We've done this stuff before, right? Well, right now we don't know what the tension is. We don't know what the acceleration is. We assume that we know the mass. If we know the mass, we know the gravitational force acting on it. But let's just kind of stop right there for right now. And think about, well, what else do we have? Well, we've also got this mass number 2. So let's take a look at what we get with it. Mass number 2. We've got the net force on mass number 2 produces the acceleration a hat 2 of mass number 2. And we've got the net force on mass number 2 is the vector sum of the force of tension T hat 2 plus the force due to gravity Fg2. And again, with these two, we have the net force produces, the net force is composed of, so we can go ahead and write that T2 hat plus Fg2 hat produces M2 A2 hat. All right, so we've got these two separate expressions for what the net force is composed of and what it produces regarding those two individual masses. And well, at this point, what we want to understand is that these two objects are coupled together, so there's some similarities in between some of these quantities here. Of course, if we assume that they're different masses, this and this will be different, as well as M1 and M2. But what about the forces of tension and the accelerations? Is there something that we can say about these? Well, the force of tension must be the same throughout the string. And I'll just say that this assumes a light string. A string that we consider massless. Why do we want to do that? Well, we don't want to get caught up with which one's elevated more than the other and how much mass in other string does it have to suspend. We're going to just use a nice little approximation that the string's mass is negligible, so we don't worry about it, and we just say, hey, the force of tension is the same everywhere in the string. What's just different is which way it acts on the individual masses. So given that this is a statement that we have that the magnitude of T hat 1 is equal to the magnitude of T hat 2, which we can just call T then, in terms of its magnitude. If it's the same, hey, it doesn't matter. What's different is, well, how it's acting on the individual masses. Both of them are up, that's great. We have to come up with some sort of way of treating that. But that's what we have with this. And, well, let's just say this. Both are directed upward. So let's not separate those words. Upward So both have the same sign regarding direction. Just say let up be plus. Makes it easiest. Hey, up's the positive direction, that makes down negative. Great. So, yeah, the force of tension, we can just represent with this T now. What else do we have? Well, we've also got ourselves the acceleration, right? We've already stated that, hey, they have to have the same characterization of changes in motion. What's different? Different directions. One accelerates down, one accelerates up at the same rate. Since they are coupled, they must exhibit the same changes in motion. Thus, the magnitudes of their accelerations must be equal, and the directions are opposite. So what does that say? Ultimately, we could say that the magnitude of A hat 1 is equal to the magnitude of A hat 2. So, great, they have the same magnitude, but if we want to go ahead and add in the directionality associated with these, all that we have to say is A hat 1 is equal to negative A hat 2. That just says opposite direction. They are equal magnitudes, opposite directions. So, which one goes up, which one goes down? It depends on which one's more massive, right? The more massive one goes down, the less massive one will go up. So, let us utilize this and this, along with that sign convention there, to see if we can rewrite these expressions here. So I'm going to go ahead and take this, change up pins here. I'm going to rewrite this expression in terms of what we just said. So we're going to go ahead and let this be up. That means this is down, right? So we can write here that FG1 hat is equal to negative M1G. The negative sign says down. Negative down. Likewise, FG2 hat is going to be equal to negative M2G. We've got the same thing there. Negative means down. T hat's up, F sub G hat's down. We're trying to figure out what the acceleration is. So with this, we can go ahead and write this one now as T. You don't have to make a distinction between T1 and T2. They're both just T, both up, minus M1G is equal to M1A1. We can write a little hat there. So we got the sign incorporation for the forces. We're trying to determine what the acceleration is. Great. Well, what we do for one, we can do for the other. So we're going to write this one as T minus M2G is equal to M2, but instead of writing A2, I'm going to take into account that, hey, A2 is the same as A1, just in the opposite direction. So we can write this as negative A1 hat, which then says that we can just write this as T minus M2G is equal to negative M2A1 hat. What we get out of this is two nice expressions that have the same acceleration, A1 and A1, and the same force of tension, T and T. T and T. Anyways, what can we do with that? Well, we can solve both of those for the force of tension. So let us just go ahead and look at this top one. Solve both for T. The first one, well, all we got to do is move that m1g to the other side. So we'll add it to both sides, and we can write t is equal to m1a1 hat plus m1g. And that's for this first expression right there. We can go ahead and take this one and solve for t as well, and get ourselves that t is going to be equal to negative m2a1 plus m2g. Negative m2a1 hat plus m2g. We've got two separate expressions here that ultimately relate the tension. The tension to mass number 1 and the acceleration, and the tension related to mass number 2 and the acceleration. T has to be equal to t. These two are equal to one another. So from this, we can say that m1a1 plus m1g is equal to negative m2a1 plus m2g. So let's just do that. So from this we get ourselves m1a1 hat plus m1g is equal to negative a1 hat plus m2g. All right, what can we do with that? We can solve this out for A1. Notice everything else is just a matter of what are the masses and the acceleration due to gravity. That is ultimately correlated with the overall acceleration of, well, in this case, mass number 1, but we know that it's the same as mass number 2, just in the opposite direction. So let us group ourselves the acceleration number 1 on one side and get everything else on the other side. So I'm going to move this over here. I'm going to move this over here. So what do we get out of this? Well, we get ourselves m1 a1 hat plus m2 a1 hat is going to be equal to m2g minus m1g. That's just rearranging that right there. What can we do with this? We can factor out this a1 hat, right? Factor it out. We've got ourselves a1 hat times m1 plus m2 is equal to, and factor out that g as well, and write this as m2 minus m1 multiplied by g. Final step, hey, divide both sides by the sum of the masses. And we get ourselves that a1 hat is going to be equal to m2 minus m1 times g divided by m1 plus m2. Here is the acceleration of mass number 1. If mass number 2 is greater than mass number 1, this acceleration comes out to be positive. We said positive's up. Yeah, if mass number 2 is greater, mass 2 goes down, mass 1 goes up. If mass number 1 is greater than mass number 2, well, we get the opposite sign, and that says that the acceleration of mass number 1 is downward. Yeah, if mass number 1 is greater than mass number 2, it goes down, mass number 2 goes up. Likewise, we could substitute back in the representation of A2 and get the same sort of correlation there. A2 is negative A1 hat, and get that. Overall, we know the more massive goes down, the less massive goes up. So generally what we'll write with this is just the magnitude of the overall acceleration. One goes up, one goes down. Whew, I'm just going to clean up a little portion here. So I'll take this off. Just write this. One goes up, and the other goes down. So we can just write the magnitude of the acceleration of either mass as A is equal to the absolute value of m2 minus m1 times g divided by m1 plus m2. Take the absolute value because this is just the magnitude. We just treat it as a positive value, and note that, yeah, the heavier one, the more massive one goes down, the less massive one goes up. So this is the magnitude of the acceleration. There we go. Nice and simple. What's the acceleration ultimately based upon? The difference of the two masses and the sum of the two masses. That's what dictates the overall acceleration, completely mass dependent. Of course, there's the acceleration due to gravity there, but hey, we need that. Anyway, what you can see here is as the mass difference gets larger and larger, you've got a greater and greater overall acceleration. And as the sum of the masses gets larger and larger, for a particular mass difference, the acceleration gets smaller and smaller. So what does that really mean? Well, it means that it's all contingent upon the masses. That's it. Large mass differences with relatively small masses will produce large accelerations. Take this for instance. What happens if M2 is much, much, much greater than M1? That is, one's like 2,000 kilograms and the other is like 1 gram. What do we get there? Well, if M2 is much, much greater than M1, the difference between them is negligible. It's approximately M2. And the sum of the two would still be approximately M2. What do we get? Well, if M2 is much, much greater than M1, this resolves down into A is equal to M2G divided by M2, which is equal to G. We get basically the free fall acceleration, which should make sense. That's the greatest acceleration that we can have with only gravity and the forces of tension acting. It'd be similar to just taking one of those strings and cutting it. What happens to the mass? It just drops down in the free fall acceleration. So that is the greatest acceleration that we can have for this system, is the free fall acceleration. And we approach it as the difference of the masses becomes very, very large. Anyways, that's kind of it. If we have the two masses are the same, M1 is equal to M2, what's the difference between them? 0. What do we get? No acceleration, because the net force will be equal to 0, and the objects balance each other out, basically. That's it. Anything in between those two endpoints, we can determine the acceleration of. And we can also start determining what the tension in the string would be given a particular mass imbalance. Because this acceleration can ultimately be put right there. And what can you do? You can solve this out for T and get what the tension in the string is acting on the individual masses. So I'm not going to really worry about that, but it's something that can be done. This is important though. How we treated this system, how we developed the expressions that overall correlate with the behavior of the system. All mass dependent. So derive the formulas here. All right, so you may see some systems that are coupled, and if they're a coupled system, you have to treat them similar to this. Look at one mass, net force on it produces this acceleration. Look at the other mass, net force on it produces this acceleration, and then unite them by the coupling factor. Their accelerations have to have the same magnitudes, and the tension in the string that's coupling them has to be equal in magnitude. And once those two things are taken into account, ultimately you do the same sort of thing. It just looks different depending on what the systems are. Anyways, if it's just a plain old Atwood machine like this, this is the go-to. If not, you gotta redevelop expressions. You may or may not see that, depending on what class you're in. All right, so that's basically it. Once this is gotten, it's just plug numbers in, which is kind of boring. Getting it in the first place, that's the more fun and insightful. All right, until next, have a good one. Be well.